Welcome back to the deep dive. We're here to take a pile of sources, research, and documentation and really just extract the critical nuggets.
All to give you the fastest shortcut to being truly well-informed.
And today, we are not just looking at a programming tool. I think we're looking at something more like a fundamental architectural decision.
That's a perfect way to put it. We are diving deep into tuples.
Tuple, right.
And if you've spent any time programming, especially in, say, Python, you've definitely used them, but maybe without realizing their specific superpower.
So what's our mission today?
Our mission is to move beyond just, the simple definition. We want to understand why this data structure is such an essential part of the coding toolkit,
What it is, how it works.
and why its main constraint is, believe it or not, actually its biggest feature.
So we've scoured the foundational texts on data structures for you, and the first thing that really jumps out is its visual identity. It's how you spot one in the wild.
Right.
When you see data values grouped together, surrounded by parentheses, that's a tuple.
That's your signal. It's a visual cue for the computer, but also, importantly, for the human reading the code.
And inside those parentheses, you have your data points.
Your data points, which we call elements, sometimes items, or even members.
And those parentheses, they're not just for decoration, are they?
Not at all. They signal a really fundamental difference in how this container behaves, especially compared to its more flexible cousin, the list, which uses those square brackets.
Okay, so let's start with how these things are primarily used, because everything I've read says they're all about efficiency.
They are. Specifically, efficiency in getting data in and getting data out.
And our sources, they really zero in on two core processes for that.
Exactly. Packing and unpacking.
All right, packing sounds, well, pretty straightforward. Is that just the act of creating the tuple, just putting the data together?
That's the basic definition, yeah. But there's a kind of subtle elegance to it.
How so?
Well, packing can happen implicitly. You might write something like coordinates, kill 10, 20, 30.
Without any parentheses at all.
Right. And the system is smart enough to see those comma-separated values and automatically pack them into a tuple for you. It's designed for this kind of quick, on-the-fly grouping of related values.
But the real magic, the place where tuples can drastically clean up your code, that comes from the other side of the equation.
Oh, absolutely. That's unpacking.
And unpacking is, I think, a genuine game changer when you first see it.
It is. It's the process where you take that packed container, that tuple, and in one single move, distribute every single element into its own separate, named individual variable.
Can you give us a concrete example of why that's so much better than the alternative?
Sure. Imagine you get some data back from an API. Let's say it's location data, longitude, latitude, and altitude.
Okay.
If that data came back in a tuple, instead of writing 3 separate lines of code like lon, data 0, lat, zeta 1, and so on.
Which is tedious.
It's tedious and it's ugly. Instead, you can just write one clean line, lan, lat, alt, data tuple, and that's it.
So you're naming the variables right there in the assignment based on the order inside the tuple.
Yeah, precisely. You turn what could have been a whole block of index lookups into a single, super readable statement. It's all about quick data distribution.
And this is actually the secret behind one of my favorite little Python tricks.
Let me guess. Variable swapping.
You got it. The old A, B, B equals B, A.
It looks like magic, but it's just packing and unpacking at work. That right side, B, A, creates a temporary invisible tuple. And the left side, A, B, immediately unpacks it into the original variables.
All without needing that messy temporary third variable you learn about in Programming 101.
Exactly. It's a perfect demonstration of its practical efficiency.
So that's incredibly useful, but whether you unpack it or not, once the data's in there, you still need ways to look inside, right?
Of course. Which brings us to our next point, member access.
So how do we get at those individual items if we don't want to unpack the whole thing? Maybe I just need the first one.
It's just like other sequential data structures. You use the square bracket index operator. So you can write coordinates SIR just to grab that X value.
And here we have to pause and deliver the public service announcement for anyone who might be newer to these concepts.
Oh, yes. The single most crucial detail about indexed access. It is zero-based, always. Counting starts from 0. The first element is at index 0, the second at index 1, and on and on.
If you forget that, you will spend hours debugging pulling the wrong item every single time.
It's a rite of passage, I think. A very common pitfall.
So we can grab items, we can unpack the whole thing, but what if I get back a really big tuple? And I just need a quick inventory. How many items are even in here?
For that, we turn to a standard utility function, Len. Just wrap your tuple in len, and it immediately tells you its length, the total count of elements inside.
Okay, that's simple enough. And what if I want to check if a specific value is present? Say, I want to know if the number 42 is in this tuple somewhere, but I don't want to write a loop to check every single item myself.
That's where the Boolean operators in and not in are so useful.
Ah, so they're optimized for this exact thing.
Completely. It's called a membership check. You can literally just ask the question in your code. Is 42 in a SQL table? And the system gives you back a simple true or false. It's incredibly fast and foundational for, validating data.
Now, we've covered getting data out and checking what's in, but here's the question that really gets to the heart of what makes a tuple different. Once I access an item,
Yeah.
can I change it? Can I overwrite that X coordinate with a new value?
You cannot.
Yeah.
And that question, that transition, leads us directly to the core philosophical difference here.
And that is?
Immutability. This is the single defining constraint of a tuple, and it's what dictates where you should use one and maybe more importantly, where you shouldn't.
So let's break that down. What does immutability really mean, not just as a word, but like in practice when you're writing code?
In practice, it means that a tuple cannot be changed in place after it's been created.
Cannot be changed in place.
Right. Once that data is packed, the tuple's structure and its contents are, for all intents and purposes, frozen. You can read the elements, you can count them, you can check for membership, but you cannot update, add, or delete them.
And if you write my tuple 1 equals 999.
You'll be greeted with a nice, crisp error from this system. It's just not allowed.
So why? Why bother with this constraint? Why wouldn't a developer just always use a list, which is way more flexible and is mutable? What's the point of a container that can't be changed?
That is the perfect question because at first glance, immutability just sounds like a limitation, right?
Yeah, purely negative thing.
Think of it like this. A list is like a whiteboard. It's designed to be written on, erased, and rewritten over and over again.
Okay, that makes sense.
A tuple, on the other hand, is like a printed receipt. Once the transaction is done, that record is permanent. If you need a new receipt with different items, you have to print a whole new one. You don't take a pen and edit the old one.
So if I have a tuple and I need a new version with just one different value, I am literally creating a brand new tuple in memory.
Precisely. You'd slice up the old one, take the parts you want, combine them with your new data, and create an entirely new object. This behavior, by the way, is very similar to how strings work. They're also immutable.
Okay, let's dig into the consequence of this, because this is where the real benefit has to be, right? Beyond just making sure data doesn't change by accident. What does this constraint actually enable?
It enables two critical things. One is about performance, and the other is about architecture.
Let's start with performance.
Because a tuple can never, ever change its size. The system knows exactly how much space it needs in memory from the very moment it's created.
Ah, so it's not guessing.
It's not guessing, and it's not allocating extra space just in case you decide to add more items later, which is what it has to do for a mutable list. This fixed known size is a real performance booster.
Okay, and the second benefit, the architectural one.
The second one is hashing. Since tuples are immutable, they are hashable, which means they can be used as keys in a dictionary or as elements in a set. Lists, on the other hand, because they can change, are not hashable. You can't use a list as a dictionary key.
That is a massive distinction. So if I need a key that's made up of two parts, like a user ID and a product ID,
you have to use an immutable structure to group them. You'd use a tuple, like userid, producted. That becomes your unique key.
So the fact that the data is guaranteed not to change makes the tuple stable. Stable enough to be used in the language's internal indexing systems.
You got it. It's an underlying requirement for a lot of advanced data management. And if you think about the bigger picture, in environments with, say, multi-threading, immutability is just a form of data safety.
How so?
Well, if you have multiple parts of your program all trying to read from the same tuple at the same time, you have an absolute guarantee that none of them can accidentally change the data out from under the others.
Because no one can change it.
Because no one can. So the limitation, the inability to change, is actually a superpower when you're dealing with systems where safety, integrity, and predictable performance are really important.
And this brings us back to what you said is their most common application.
It does, using this safety feature when you're transferring data.
So if they are so safe and fixed, where do they absolutely shine in just day-to-day coding?
The primary application is something we touched on earlier, functions returning multiple values. The mechanism is just so clean and fundamental to the language.
Walk us through that again, but this time let's focus on the integrity piece.
Okay, so a function does its work, And at the end, it executes a return statement if it lists multiple values separated by commas.
Like return balance, status code.
Exactly. The system doesn't return two separate floating objects. It automatically packs those values into a single tuple and returns that one container.
So the function is really returning balance status code as a single atomic object.
Yes. And the code that called the function can then immediately unpack it.
Yeah.
Amount, status, my function.
And because the result is a tuple, it's a clean, safe envelope for that data transfer.
It's an envelope. That's a great word for it. You have the guarantee that the status code hasn't been accidentally changed by some other part of the program before you get a chance to check it.
So this really does demonstrate the core trade-off we've been talking about. The immutability feels like a constraint.
A serious constraint. If
Yeah.
you need to manage a list of things, that's always changing.
But that same constraint is what enables the simplicity, the data integrity, and even the architectural necessity for things like dictionary keys and safe function returns.
And that's the summary right there. That's the core knowledge nugget we've extracted. Tuples are these essential immutable containers in parentheses.
Optimized for quick grouping
That's the packing.
and efficient data distribution.
The unpacking. Their fixed nature isn't a bug, it's a feature. It grants them memory efficiency and the power to be stable keys, making them just ideal for safe, reliable data transport.
And for you, the learner, the key takeaway here is that choosing a data structure isn't just about syntax. It's about predicting how your data needs to behave over its lifetime.
Absolutely. If your data set is fixed thick coordinates, configuration settings, database primary keys, and you value speed and safety.
The tuple is your go-to architectural choice. If you need constant modification, adding and removing things, you look elsewhere.
Which leaves us with a final thought for you to mull over as you explore this balance between flexibility and reliability.
Okay.
We talked about how immutability is great for safety. But let's think about memory management. When a list grows, the operating system might have to find a whole new, larger chunk of memory and copy the entire list over.
Right, because it ran out of room where it was.
Exactly. So given that a tuple can never change size, how does this fixed one-time memory allocation fundamentally simplify and speed up memory access compared to those constantly resizing mutable structures? Think about the underlying physics of how a computer actually stores and retrieves data.